Welcome back. This is, we're going to call this part 2 of this particular series of videos where we're looking at breaking the octet rule. We had said earlier that when we're dealing with the octet, what that is we're dealing with 8, that concept of 8 electrons, right? Valence electrons that are in some sort of valence orbital sharing pattern in some way, either lone pairs in that domain or the overlapping or valence orbitals, right? So let's take a look at another one. Another example that I'd like to sort of focus on would be something with a slightly different geometry than the previous lesson. In the previous lesson, again, I'll have a link to that or somewhere up here or whatever, or you can just go to the playlist and it'll be there waiting on you. So phosphorus pentachloride. All right. So let's take a look at this one. This is going to have, I chose this one because it's going to have a different geometry than what we normally see, and it's different. It'll be a different geometry than the previous example that we had. So phosphorus pentachloride, if we were to take a look, so phosphorus, we have one of these, and there's what, 5? So if we go to our periodic table, there's phosphorus. We can see it's right underneath nitrogen, so it would also have 5 valence electrons, right? And so there's one of those times 5, and then chlorine, remember we go to periodic table, there's chlorine, group 7, 17, depending on which numbering system you're looking at. So there's 7 valence electrons, right? And so there's 5 of these times 7. Well, that's 35 plus 5. So we need 40 electrons total, right? All right. Well, let's see what we can do. This is one has more valence electrons than what we're normally working with. So remember, things they're repelling and going in a very orderly fashion, right? And so we want to try to put 5 out here in a way that's kind of, I don't know, we want to put 5 out here in a way that would look like everything is spaced sort of as equally as possible. So, I mean, if you look here, that's an angle, that's an angle, that's an angle, that's an angle, and that's an angle. And the way that we're drawing this right here, the angles look equal, right? If we were to look at this as sort of the central region where the vertices is, then all the angles, right? If we go out from there, we could say that the angles look pretty equal. And that's what you're shooting for. Whenever you draw any of your bonds, you want to try to represent as best as possible as the three-dimensional geometry that exists, okay? So here's 5 bonding domains. Well, let's add some chlorine, right? Let's add some chlorine. Starting to look a little different here. Now let's fill in our octet, right? So we've got lone pairs here and here, 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 right? Fill in your octet. Complete your octet, and let's see what happens. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, plus 2, 4, 6, 8, 10. There's our 40. We're good to go. All right. So let me back up all of this. Let me get rid of all of this. Get out of the way. So there's our geometry. There's our structure. It's just an expanded octet. And so remember, now we use formal charge. Let's verify, is this going to work, right? So formal charge on the phosphorus, and we're going to go formal charge on the chlorine, right? And so remember, phosphorus group 5, right? I'm kind of thinking, yes, phosphorus is group 5, chlorine group 7, right? So phosphorus group 5 minus the number of electrons that are in lone pairs, we see that that's 0, minus half the number of electrons in bonds, that's 10. So 5 minus half of 10 is 5, so that's 0. So central atom's carrying a zero charge. So far this is good because remember, there's a zero charge on this particular molecule. So that needs to be happening. So chlorine, they're all single bonded, all 3 lone pairs. So whatever math we do here, the charge applies to all of them. So group 7 minus group 7 minus the number of electrons in lone pairs, that's 2, 4, 6, minus 1 half the number of electrons in bonds, only 1 bond, so that would be 2 electrons. So 7 minus 6 is 1, half 2 is minus 1, gives us 0. Formal charge is verifying that this works. This is a good structure. So here's our expanded octet. Now we had just ask ourselves, okay, here's our formal charge. We've verified this. Now, how do we draw this? How in the world are we going to draw this thing? So here's where you go back to your VSEPR document that I've given you. And you can see here the first things here are just through this domain of 4, right? Well, that doesn't do us any good. So what we've got to do is we're going to scroll down, and we can see that here I show you some more geometries. If we go further, remember all this is polarity and stuff like that. There's some other geometries. Go 1 page further, and here's where we get into the good stuff. So you can see here, there's the first 4 geometries with the 2, 3, and 4 domains. But we have 5 domains. So here you come down, and it's going to be one of these 4 right here. It's either going to be trigonal pyramidal, it's going to be seesaw, it's going to be T-shaped, or it's going to be linear. So we ask ourselves, what are we working with? Well, we are working with, I want to make this a darker color for you. We are working with phosphorus pentachloride. So if you think about that, here is our A, and here is the X. So we're dealing with an AX5 formula type, right? Well, if you look at this, that's AX5 because there's a central atom, and then there's 1, 2, 3, 4, 5 regions of space, 5 domains around that central atom. So we know that that's going to be our geometry. Just a quick side note. If we were to look at seesaw, we can see that there's a central atom, correct? Then there's the 1, 2, 3, 4, so that's AX4, and then the lone pairs are here, so that would be E. T-shaped would be AX3, E2, and then linear, there is a linear because you can see that right there is the linear part of the bonding, right? So that's what's being looked at as far as that goes. But then you remember you still got your lone pairs here and here, so that would be A, there's 2 X's, and then there's an E3. So just a side note, I wanted to help you out because I know this part is new for some of you. So we need this right here. We basically need to put the phosphorus in the middle. We're going to draw one of those phosphorus coming at us. That's what the wedge is, one going back and then off to the side, right? So draw something that looks like a T, right? So we come back here, and we've got our, oops, I forgot I'm still on that blue. So we've got our phosphorus. And then remember we had something going like this that had the chlorine. And then remember there was a wedge and then a dash. That's it. I'm going to change this back to my light color blue. I like having that. So that's our molecule. And remember, if there's wedge and dash, we avoid putting the lone pairs on the molecule. It's assumed that they're there just because it can get cluttered, and sometimes it can take away from being able to view the three-dimensional geometry. So now what I've done is for for you to be able to help see this a little bit better, here is something that is, here's a geometry that is A, X, 1, 2, 3, 4, 5. And then here I've put these to represent where the lone pairs are. And these are on all of the chlorines. So remember, so the green is chlorine. This light purple represents phosphorus. And so it has 5 bonding domains. So just for the sake of training, I put those there so you could see that. But now you just visualize that they're on every one of these chlorines. But you can now clearly see there's the central atom. And so depending on how you rotate this, you can see that there is always one of those chlorines that's sort of coming at you. So this chlorine right here is coming at you. Depending on how you're viewing this right now, I'm trying to go in reverse, but you might see that this one's going back behind you. So I'm going to rotate this a little bit so that it might a little more better match what you have on the screen. And so this is coming at you. This is going back. So there's the dashed line. There's the wedge. Here's the one on the side, and here is our linear form right here. All right. Here's our linear form right here. Not too bad, right? So now let's take a look at this. If you think about it, we have 2 different types of angling that is going on, right? So if we ignore the one on the top and the bottom, just pretend that they're not there, you can see that there's a geometry there that we've seen before, right? And right here, this is an angle of 120 degrees. This right here looked like a trigonal planar just by itself. Just by itself, it looked like that, right? So now if we put this back on, if we put these back on, and then we were to ignore these right here on the side, so I'm going to take them off just for a second. You could see that that from here to here, if we were to look at it, that's 180 degrees if there was nothing else there. But there is something else there all the way around this. Now, half of 180 is 90, so you realize that that's a 90-degree angle right there. So there's a combination of the 2 angles. We have those, and then right here we have this 90-degree angle. Okay? So there's 2 geometries. So now, remember, we go back to VSEPR theory. That's trigonal bipyramidal. All right, so remember we said this was AX5. We've got trigonal. Oh, that's pretty bad. Bipyramidal. Okay, and then electron domain is it's the same, right? Electron domain is trigonal bipyramidal. So just like domain of 4, the electron domain was tetrahedral, and then the geometry could be tetrahedral. So where you have 5, the domain is trigonal bipyramidal, and then the geometry here is also trigonal bipyramidal. And then if you happen to have 6, which we will have examples with 6, problem sets I've given you have had 6, I'll do a video where we have 6, so I can just sort of show that as well. You can see here that you get multiple geometries again, and so that's where all these different names come from. But if you have 6, then the domain is octahedral, and you can have a geometry that is also octahedral, right? So, yeah, there you go. There you go. Octet rule, expanded octet, being broken. So go do some practice work. I hope this helped. There's another good one. You get into all sorts of interesting geometries. So I'm going to do some later videos where we look at how geometries like this are really important for biological functions, right? That's going to be a neat video. I'm working on a few ideas of those that I think will be very helpful for you. Maybe put some perspective on things that you've studied in your earlier studies of biology or whatever. All right. Always great to see you. Great to learn with you. I appreciate you being here. Stay curious. Go work on some problems. Definitely get yourself some coffee while you're doing it. I'll see you in another lesson soon. Bye.